We recently explored the least upper bound property. Today we will see a most powerful consequence, the Archimedean property. Intuition tells us something simple. Small steps can cover any distance. If you have a tiny step size x and a massive goal y, you can always march past that goal eventually. But in rigorous mathematics, we cannot rely on intuition alone. Without the least upper bound property, infinite numbers could theoretically exist, barriers that no amount of finite counting could ever reach. We will rigorously prove that such barriers are impossible in the real numbers. Let's visualize exactly what this means. We take steps, 1x, 2x, 3x, stacking them side by side. The theorem guarantees that no matter how far away y is, there is some integer n where our stack finally crosses the line. To prove this rigorously, we use proof by contradiction. Let's assume the theorem is false. This would imply that there is some goal y that acts as an unbreakable wall. It implies that for every integer n, our step nx stays trapped to the left of y. Mathematically, this means the set A, containing all our steps, is bounded above. Here is where the machinery of the real numbers saves us. Because R has the least upper bound property, this bounded set A must have a sharpest edge, a supremum. Let's call this limit alpha. Now, we use the definition of the supremum against itself. Consider the point alpha minus x. Since x is positive, this sits to the left of the edge. Because alpha is the least upper bound, nothing smaller can be a boundary. So, alpha minus x is not a barrier. This means there must be some step, nx, that jumps past this point. Now, take one more step. Add x to both sides. On the right, we are left with just alpha. On the left, we get n plus 1, x. This is simply the next step in our sequence. We have found a member strictly greater than alpha, but alpha is the maximum. This is a contradiction. Our assumption was false. The Archimedean property is true.